Alrighty, welcome back to 105. So, we had so much fun with recursion in the last lecture, we'll do it again, just like recursion. Alright, so, just as a recap, just to drill it into your head, a recursive function is a function that calls itself. In order for it to terminate and do useful things, we need at least two things. We need a base case as the first thing, which is just a simple solution that we know. And then we need, as the second thing, a recursive step, so reducing the problem to a smaller version of itself. So we'll have more examples of that today. In fact, with recursion, we don't even need anything fancy like a loop. So, one thing that's commonly a bit easier to do recursively than it is iteratively, or in other words, using a loop, is computing the greatest common divisor between two numbers. So, the greatest common divisor of two numbers, or two integers a and b, is the largest integer d, such that it is a divisor of both a and b. So, bunch of different ways to solve this, but there are actually some algorithms, and one of the simplest ones to implement is done recursively. So for this, we'll just assume all integers are positive and greater than 0. So one of the algorithms for it, we don't really necessarily have to get into the math of how this works, but just how we actually implement it. So there is something called the Euclidean algorithm for finding the greatest common denominator, or divisor. So to find the largest common divisor, d, of integers a and b, if a is greater than or equal to b, then we can replace the greatest common divisor of a and b with the greatest common divisor of b and a mod b. So we're just dividing a by b, getting the remainder, and doing this until finally the GCD we get an argument where b is actually equal to 0. And then once we make it to this step, which as you can guess is our base case for this algorithm, we know that d is the GCD, and that is the solution to the problem. So we can write that out recursively, just given that algorithm. There's only one little trick. So if we go here, we're writing GCD given an int a and an int b, and then we have our base case at the top. So our base case is if b is equal to 0, then our greatest common divisor is just simply a. And then this is our recursive case at the bottom. So given what the algorithm says, this is only valid if a is greater than or equal to b. Then we return the greatest common divisor of b, and then for b we replace it by a mod b. So if we just implement it directly, this isn't going to work because, well, we could actually call this with a less than b, in which case it will fail because we'll make it to the end of GCD, and we'll just hit the end of the function with no return statement or anything like that. We'll get a default undefined value, and then our program will not work. So in order to do that, in order to transform the problem such that that thing always happens, all we have to do is flip them around. So in this case, if we have a is less than b, what we're going to do is just swap a and b. And to do that, I don't need to write a swap or anything like that. I just change them for the recursive call to GCD. So I just swap the arguments around so that recursively it would call itself with the arguments swapped around. And now it would fall in this case and reduce the problem to a smaller version of itself. So that is also something you can do with recursive functions. Your recursive step doesn't have to necessarily break the problem down into a smaller version of itself. Just at least one of the steps should break it down to a smaller version of itself, which is this case. And then for the rest of the program, I don't want to write scanf or anything like that because I don't want to hit enter a whole bunch of times and show display messages. So I'll just write this program such that it just takes 2 integer arguments. So make sure that I get 3 arguments in this array of C strings. So the first one is the name of the program, which I don't have to use. And the second one I'm expecting to be an integer. Third one I'm expecting to be an integer. So I can use this a2I function we saw in the strings function lecture to convert that string to an integer. And then check that it's actually valid. And then we can just print off the values of A and B we got, and the result of the greatest common divisor of A and B. So that was the whole trick. So if we compile and we run this and we give it the arguments 20 and 8, well, the greatest common divisor between these is actually the number 4. So it's not 8. So if we tried this smartly and not doing the recursive thing, well, you would try just the smaller number, see if it divides by the larger number. If so, then use that one. Otherwise, you can go through all the divisors of the smaller number and see which one is the greatest common divisor. But I could also do it recursively like this. So I can see that it works. The greatest common divisor of 20 and 8 is indeed 4. And this does work if I flip the arguments around. It will just cause an additional recursive function to happen, or a recursive call to happen. So, any questions about that fun thing? So, also, if you want to step through it, how it would work with the 2 arguments is first, we would call GCD of like 20 and 8. And what that's going to do, when we execute that, that's going to fall into the recursive case where A is greater than B. So it's going to call GCD with the first argument as B and the second argument as A mod B. So it will be 20 mod 8, which the result of that is 4, right? So the result of that is 4. So when we are evaluating this function, GCD of 8 and 4, it will have its own copy of variables. So remember, each function call has its own copy of variables, where now A is equal to 8, B is equal to 4. So when we go here, this will also be the recursive case. And we will go ahead and get 4. And then 8 mod 4, or sorry, yeah, 8 mod 4, which is 0. And then that's the call we would make to GCD. And then in this case, B is equal to 0. So we're going to hit our base case and return A in this case, which is 4, which will just go up, start letting everything return. So the result of GCD 4, 0 is 4. That means the result of GCD 8, 4 is also 4. And the result of GCD 20 and 8 is also 4. All right. Everyone okay with that? Lots of fun. All right. Well, let's try something different then. All right, screw a loop. Let's just try to count to 5 recursively. So this might take a bit of thought. I'll give you some time to think about it. So we are writing a function called count that takes a single argument, int n, and given the n, we want it to go ahead and just print the numbers. Oops. Yeah, we want to go ahead and print the numbers. Let's say we want to count from 1 to 5. So when we run this, it should output 1, then 2, then 3, then 4, then 5. So when we are writing it recursively, we are not allowed to write a while loop or for loop or any loops whatsoever. So I'll give you a minute to think about how you might write this function such that count recursively counts up from 1 all the way to 5.
Oops.
Alrighty, any ideas how I should write this count function? Anything at all. Even better if it crashes or something. Well, probably not if it crashes, but if it gets weird output, that's fine. Any help? Yeah. Yeah, so we could have a printf somewhere. So printf, probably just the number itself, right? So that's a good thing to start with. Yep. Yeah, so call count n minus 1, so just like that. So this sounds like, oops, if we were to label it, this is my recursive step. Okay, what else do we need? The base case. So what's our base case? N is equal to 1. Okay, so if n is equal to 1, then what should we do? Print 1 and just return? Yeah, so we could just print 1. So let's just print this. And then just return. So that should just go ahead and end my function. So everyone like that? Yeah?
So here, it would print out 5 first, right?
Yeah, well, the question is, won't it print out 5 first? So let's go ahead and try it. So let's compile it. It's called count, so let's just run count. Whoops. Yeah.
So I think maybe what we can do is print that, send it to D, and then the argument that would be count and then minus 1. And then if your base case is n is equal to 1, then return 1.
So you want it to do what? Sorry, you want it to return?
So you say printf, right? And then in the argument,
Yep.
you replace the argument n with count of n minus 1.
So replace n of minus 1 by another count of n minus?
Like in the printf.
Oh, in the printf, do count of n minus 1 instead? So we can't quite do that because count doesn't return anything, right? So we just want count, the count function to just print all the numbers. Yeah?
It changed the base case, like if n equals 0,
If n equals 0, okay.
you return,
Okay, so if n equals 0, we just return, yeah.
and then you switch the count and
Yeah, switch the count and the printf like this, right?
yeah.
Yeah? So let's see if that works. So I do that. Hey, it seems to count. So why does that work? Well, in this case, our base case is if we don't have to, if there's no numbers to count, we don't have to count anything, right? So we don't have to count anything. So that's one of our base cases. In this case, it doesn't matter. We could just, if it's 1, we could just count 1. Turns out it doesn't matter. So if I move this here and change this, compile and run it, nothing's going to change. It does the exact same thing as before. I just have to write 2 printf statements. Doesn't really matter. I would argue that in order to repeat less, this is probably the easier one. So then if n is 0, I don't have to count anything, right? That's a good base case. And then my recursive step is, if I'm reducing this to a smaller version of itself, let's consider the case where n is equal to 5. If n is equal to 5, like instead of just thinking about what order should I put, printf in and count, what will give me what? Well, if I'm counting from 1 to 4, and currently n is equal to, if n is equal to 5, right, where I should be counting 1, 2, 3, 4, 5, and I'm breaking it down into a smaller version of itself, well, when n is equal to 4, what I assume I already have, this should actually just print 1, 2, 3, 4 if it's implemented correctly, right? So whenever I see, in this case, count of n minus 1, I should just replace that by assuming count of 4 works. So that means it should come before the printf statement because it will print 1, 2, 3, 4, and then what I should add to it in this one single step is I should just print the number 5 at the end, right? That will get me 1, 2, 3, 4, 5. If I do it in the opposite order, if I do it in the opposite order, what I'm doing here is in my recursive step, I'm printing first. So if I print first as n is equal to 5, I'm going to print n first. I'm going to print 5 first. And then what I actually did is, the problem is I actually implemented the reverse. I implemented counting down. So the rest of this will actually count down is what I accidentally wrote as my smaller problem because the number I'm currently printing in this step comes first. So it'll go 5, then 4, then 3, then 2, then 1, then return and unravel, and then return from the main count function. So if I put it in this order, not quite right, because again, I am now counting down. If I want to count up, assuming that this actually works correctly, so this should go from 1 to 4, well, I should print off 1 to 4 and then have the printf at the end. So 5 should come at the end. Yeah?
So each time you put print before, each time the function calls itself a print, right? That's why it's going to class the preaching out.
Yeah.
So once you hit the base case, just nothing happens then?
Yeah. So how this is working now, how it's written. So if we step through all of the different function calls that happen, first we called it with count of 5, right? We call it with count with n equals to 5, so that doesn't go in the base case, it goes into the recursive step. So first thing, count of 5 is going to call count of 4, right? Because that's n minus 1. So it'll call count of 4, and then before that returns, that will go into the recursive step, call count of 3, then count of 3 will do the same thing, call count of 2, then count of 2 will call count of 1, and then count of 1 will call count of 0, and then this function will hit the base case, right? So this will hit the base case and return. So count of 0 will return, so it will return and we'll go back to complete the latest function call, which is count of 1. So it would continue from this line, right? So then it would print in count of 1, n is equal to 1, so it's just going to print 1. And then implicitly there's a return here, right? Always remember that. Oops. So then, whoops, apparently I can't write. And then we'll return. So count of 1 will be done, then count of 2 will continue, n is equal to 2. It will go ahead, print 2, then return, and then the rest of them will do that. Yeah?
So after the base case is reached, like how does C-Notice skip over the count n minus 1?
How does it know to skip over count? It doesn't skip over count of minus 1. It continues from it. So it's like a normal function call, just, yeah, just count of 5 is calling count of 4, count of 4 is calling 3, 3 is calling 2, 2 is calling 1, 1 is calling 0, 1 returns. So we resume from where we left off in 1. It finishes, and we resume where we left off in 2. Then we resume where we left off in 3, just like any other normal function call. Yep. So in this case, right, whenever we hit count of 0, we did nothing, right? So we did nothing here. And then it returned from count of 1, and then count of 1 printed 1, right? So if I change this, my base case, if I just simply say when it's 1, just stop, that won't work because when I do this, it'll go into the base case and then return without printing anything. So that's why I'm just doing the same thing here, right? So yeah, so now because my base case is 1, this call of count of 0 will not happen, right? So we'll only make it this far, count of 1, it will print off 1 and then return, and then we'll be done. If I wanted to, I could make a crazier base case, right? This will also work if I do, let's say I hard code things. Say my base case is 3, and I just do something like, oops, this. So I just do 1, 2, 3, right? That'll also work as my base case if I want. So it would just call, count of 5 would call count of 4, which would call count of 3, and then 3 will print 1, 2, 3, which is what I expect, and then they'll add a 4 and then add a 5, so it will still work. But usually this is kind of a crazy base case because, you know, it works, but if I did something now where I said n was equal to 2, now that's not covered by my base case, right? So now if I do something like this, ooh, yikes. Out of memory, or I messed up my stack or something like this because, well, it'll go n of, when n's equal to 2, that's not the base case, so I'll do the recursive step, go call 1, then call 0, then call -1, then -2, then -3, then -4, until I assume that's a Stack Overflow. All right, any questions about that? No, that was a stretch. Okay, all right. Also for practice, most of these problems you can actually compute iteratively well. If you look at the example, I give an example of how to do this, or sorry, how to do the GCD also iteratively. All right, so something else we could do, we could compute the sum of an array recursively. So we could use the exact same 2 rules for this as well if we want. So if instead we're trying to compute the sum of, the sum of the array recursively, well, we should be able to do that if we can break it down into a smaller version of itself. Anyone think of what my base case and my recursive case should be if I am summing all of the elements of an array? Yeah. Sorry? Yeah, so good base case. I mean, some options here. Base case is like if the array length is equal to 1, then the sum is just what? Yeah, the first element, which is just array of 0, right? All right, that looks like a good base case. Everyone like that base case? All right, what about my recursive case? For calculating a sum. Yeah. So just sum of the array, like sum of the what? Sum of the array. Array length minus 1. Plus array length minus 1. Something like that. Everyone like that one? Yeah. Yeah, so this could be our base case of array is equal to 1. Or if we wanted for some, in this case it's yeah, it doesn't actually cover the case if the array is empty. It's up to the question whether it specifies if that's a valid input or not. So if it said the array has to have at least one element, this is good. If it says the array can be empty, we probably want to consider the worst case scenario, in which case we could just say if the array length is 0, just return 0, right? And then the array length of 1 is also covered, right? So in that case, sum, if the array length is 1, we'd get sum plus array of length of 0, and then this would be, if array length is 1, 1 minus 1, which is 0, so it'd still add the first element. So if we compile and run this, oh, and also we're taking the sum of 1, 2, 3, 4, 5, so the answer should be 15. So it does indeed work. So questions about that one? Another fun recursive solution. So bunch of different ways to write it. This recursive case was like taking the sum of the first n-1 elements and then adding the nth element to the back. I could also do the other one where I keep the first element and then try and sum up the rest of the elements. So to do that, also a perfectly good solution. It's just going to be slightly different. If I do that, the element I'm currently looking at is array 0. And then for sum, if I'm summing the rest of the array, I have to do a bit of ugly pointer arithmetic, right? Because array is just the start of the array. If I want to move an element forward and move to the next pointer, I have to remember to do array plus 1. So that will move that array to point to the next element. And then we still consider the array length as -1. And then we can get rid of this. So this is also a perfectly good way to do it. Again, multiple ways we could break the problem down. If we compile and run it, still works, still 15, but your solution's probably better because I didn't have to remember to do that array plus 1, right? If I don't remember to do array plus 1, here, oh, good question for debugging. If I forgot to do this array plus 1, what's going to happen? Yes, it's going to add the first element, in this case, 5 times. So in this case, since I don't move it, if I compile and run it, the answer will be 5 because I'm just adding the first element 5 times. So I'm doing the correct number of steps in this case. I'm just doing it to the wrong element each time. And my sub-problem is a bit messed up in this case. So there's also different ways to write it. This is not the only way to write it. Another common way to write it is, well, maybe, again, remember the tail recursive thing? We could write it like this. So we could add another variable onto this. So we could add another function argument that's keeping track of the current sum we have calculated so far. And then our base case can change slightly. Again, if this doesn't come up naturally to you, don't worry about it. As long as you have a solution in this course, it's good enough. But in this case, if my base case is now if the array length is equal to 0, just return the sum I've computed so far. Otherwise, in the recursive case, I do the same thing I had before. So it's array plus 1, array minus 1, and then the current sum is equal to the first element plus the current sum I have so far. And then this is, like we saw before, the tail recursive version of this, which could be optimized to just a loop by the compiler. Again, you don't have to actually know that. But sometimes when you think of recursive functions, you might be able to solve it if you just add on another argument. So a common thing we do is go ahead and if you're implementing sum that doesn't take that additional argument, you just create a function called whatever the name is underscore helper, just a normal name that we use. And then in sum, you implement it in terms of helper. So in my case, if I don't want the user to specify the current sum because the initial value actually matters, right? It's what should be returned if there is actually 0 elements in the array. So maybe I don't want to make it easier for my user to use. So I can implement sum in terms of sum helper. So I can just return my recursive function, sum helper, give it the array length, and then the current sum equals to 0. And this version is equivalent to what I wrote before, so it's called sum helper. We get 15. All right, any questions about that till we move into a fun game? Okay, so let's do something way more fun. All right, so how many of you have heard of the Tower of Hanoi before? Some? 3 people? 4 people? 5-ish? All right, so there is this fun little game called the Tower of Hanoi. So how it works is there's a tower of disks of different sizes, and there are 3 rods. We'll call them creatively rod 1, rod 2, and rod 3. So the goal of this game, if you want to call it a game, is to move all 4 disks from rod 1 to rod 3. It has 3 rules. So we can only move 1 disk at a time. So we can only move 1 disk at a time. And you can only move the top disk from a rod and place it on top of another rod. So you can't try and sweep it in at the bottom or anything like that. And then the last rule is you cannot place a larger disk on top of a smaller one. So these are ordered by size. So 1 is the smallest, 2 is the biggest, or 2 is bigger than 1, 3 is bigger than 2, and 4 is the biggest one in this case of all of them. So this is our problem. So let's go ahead and, whoops, not that. So we can see it's called Hanoi Tower. Let's see if we can see that. Let's see the age. So the age there at the bottom, whoops. Why are we tracking? Oh no, come on camera, you can do it. All right, that's me. All right, so if we don't see it, the age at the bottom there is, where are we? 36 months and above. So 3 and above, we are all of age, so we can play this game without choking on something. So if I start choking, you might have to save me, but hopefully not. So here it is. Same thing, except they're more fun colors. So this is what we are trying to solve. So we are trying to move all 8 of these disks from this peg to this peg. Let me flip it around for you so it's this way. All right, so I have to do it backwards. All right, so if we're trying to understand this problem, easiest thing to do is to just start at the simplest case. So let's just move a bunch of these all around. So simplest case, if I want to solve the problem where I move a single disk from rod 1 to rod 3, how do I do that? Yeah, I move it here, right? That was easy. So didn't break any rules. Probably not that fun. So let's try it with 2. All right, if I do it with 2, I have to move this disk because it's the only thing I can validly move, right? It's at the top. Where should I move it to? Votes for 2, votes for 3. All right, no one thinks I should move it to 3, so I should move it 2. Then this here probably, right? And then this here. That looked all right. Anyone see anything recursive there at all? Probably not. Let's make it a bit harder then. All right. Where should I move the green one to? Should I move it to rod 2? Votes for 2. Remember, this is a game for babies. So, okay, votes for 3. All right, 3. Okay, so if I move that to 3, well, I can move this one. That's probably not that useful because I just moved it. This one, well, I can't move it here, right? Because this one's bigger than this one, so I have no choice. I have to move it here. All right, where's the green one go? On top of the light blue one to 2. Okay, then this here. Okay, now what? Green to 1. Blue. Okay, did we see anything recursive there? No? All right, go. So this goes where? 3? 2? Light green on 2? Blue. Green goes to 1. You can't flip it around. All right, so we screwed it up a little bit. So, babies are smart these days, huh? So 3 again. We did what? What did we do? We did this, 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 this. Okay, so that seemed to be easier. All right, so here. I should be able to do this and see if you see anything recursive. So I believe this is, which one goes first? Let me think. So 1, 2, 3, 4, 5, 6. Whoops. Reset. All right, sorry. 1, no, that's not right. Sorry. Okay, let's see if I can do this. Yeah, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, did you see how to solve that recursively? There. Okay, to visualize it better, let's do this. So, to think about it recursively, right? If I'm thinking about it recursively, what's my smaller problem that I can actually do? Well, if I'm trying to move 8 disks from this to this, well, I should be able to think about it in terms of 7 disks, because this is like just a smaller version of the problem, right? This is just 7 disks. So if I'm solving this in terms of a stack of 7 disks, what should I do? So if I could just take up 7 and not drop them, where do I move these? To 2, right? So that was a smaller problem. Then what do I do with the one I'm currently trying to solve? Move it to 3. And then I could take my giant stack of 7 and move it here, right? Did that look recursive to anyone? Sure did. It looked very recursive. Yeah, what's that in the back? Yep, so that was our recursive problem. We did it in terms of 7. So all we have to do to solve that is just write it up. So how I can write this in code is if I want to solve the Tower of Hanoi, all I have to do is I'm trying to solve it for, in this case, however many disks. I'll call int disks, and then I'll just number my rod something. So I'll say int from rod. So initially that's going to be 1. Then 2 rod, where I'm moving the mul 2, which is going to be 3. And then I'll just call the other one the spare rod, which is rod 2. So if I'm trying to solve it for however many disks, well, I'll just print off how many disks I'm solving it for. And then this Hanoi function should return how many steps it takes to solve this problem. And as more fun, we'll print off what we're going to do in each one. So here, the from rod initially is 1. We're moving it to 2. And then we're moving it to, or we have 2 as the spare rod. So if I'm solving this recursively, what's a good base case? Yeah. So n equals 1, or if I didn't, probably a better case that's easier is just if there's no dis at all, right? If there's no dis at all, I can use that as a base case too. So if dis is equal to 0, then I don't have to do any steps, right? I'm already done. So that's my base case. So for the recursive step, so in terms of numbers, right? My recursive step is to take this pile of n minus 1 that's currently on rod 1, take this stack, put it on rod 2, take the disk I'm currently concerned about, go to disk, that goes to disk 3, then I take the pile that was on disk 2 and throw it all on disk 1, right? So if I wanted to program that, which this program is way easier to do recursively, my recursive step is, well, I could say int steps equals Hanoi. So my problem is dis minus 1. And then currently, all these dis minus 1 are also starting on the from rod, right, which is initially rod 1. I want to move them all to this current spare rod, and I can use the 2 rod currently as a spare. So I can do something like that. So they all start on the from. I'm using the 2 rod. I'm moving that whole stack to rod 2, which is my spare. And then that means the original 2 rod I can just use as my spare as I'm doing that. And then here is the one step I'm doing. So my one step I'm doing is just move disk, the current disk I'm looking at, to rod, whatever rod I'm trying to move it to, right? So I'm moving disk to rod. And it's just called disk. So I'm moving disk, whatever disk currently is, to the 2 rod. So that is the step of just doing, so I've already done this, then that's the step of doing this, and then now the rest of that is just to move it currently from that spare rod to the 2 rod. So when I do this step, that steps plus equals 1, because plus equals 1, because I just moved the big disk to rod 3, right? And then the final step is steps plus equal Hanoi. I still have disk minus 1. They are currently on the spare rod, and I want to move them to the 2 rod, and then I can use the from rod as my spare rod. And then at the end, I just return the number of steps. Everyone kind of see that, how it relates to how I just did it? Yeah. So why do I have to call it twice? Because when I did it recursively, so the first recursive call is this. So I'm moving this giant stack here. So that's my first recursive call. I'm moving the giant stack to rod 2, sorry. So this is my first recursive call. And then I'm doing this step. And then I'm doing this as my second recursive call. So you don't have to just have one recursive call. You can break down your problem. I broke it down into 2 versions of a smaller problem, right? So this stack, this giant stack moving here. Whoa. No. Oh, well, whatever. Same idea. I'll pick that up later. Oh, it just hit my laptop. All right. Anyways, that's the whole implementation of it. So if we run it now, with 4 disks, I did it in 15 moves, right? So let's see. So Hanoi of 4 disks. So if I do run it, it does tell me all the steps and the fact that I did need 15 steps. So it's telling me exactly what I did. So I'll move disk 1 to rod 2. I did that. Then disk 2 to rod 3. Then 1 to 3. Then 3 to rod 2. So that's the end of my first, that's not the end of my first case. Then I move disk 1 to rod 1. oh wait, yeah, that was the end of my first case, right? So I finally moved disk 3 over. Then here I moved disk 1, disk 2, then I moved disk 1. Then I can finally move my disk 4. So this took 7 steps, this took 1 step, and then we had another 7 steps. So now we can finally solve the problem. Let's see. So, any guesses how many steps it takes to solve this? So this is 8 disks. And remember, 3 years or older. Well, thankfully we wrote a program so we can see. So, let's see what it takes to solve 8 disks. 255 steps. I guess parents just want their babies to be occupied. So, if you really wanted to, keep your baby occupied, or your toddler, I guess, well, how many steps will it do to take 9 disks? Well, let's see. Whoops. 511 steps. So if you really want to keep your baby occupied, give them a rod with 20 sticks. So how many steps would that take at minimum? Yikes. So yeah, in general, it's to the power of the number of disks minus 1. So you can see how, they keep children occupied back in the day. Very effective. If your child's too smart, give them another disk. It'll take twice as long to do it. And if they screw up at any point, well, they'll probably take even longer than that. So that's fun. This is a version that is easier to write the solution to recursively. It's actually quite nice to write the solution to recursively. You could write a solution using a for loop or a while loop if you want. I challenge you to do that because it will be a lot more complicated than that, and you will probably get it wrong at some point. That one is easy. So with that, we have solved a child's toy as promised. So just remember, pulling for you, we're all in this together.